Hi everyone, good evening. Thanks so much for tuning in again. This is a continuation from the last video. We went over just the reactions and just the pathways and the steps of glycolysis very briefly. Even though unfortunately, it was a 24-minute long video, I kind of got sidetracked here with how I wanted to bring this to fruition. However, we're just going to make separate videos for all of these, like pathways and stuff in the chapter, and then talk about the notes more in depth later. So this one's going to be gluconeogenesis, when we're going to be replacing or replenishing the glucose stores of the body. So gluconeogenesis actually has 11 steps. Most of them are similar to what we saw in glycolysis. However, we do have some differences here. We have to kind of focus on these steps from glycolysis. We have to focus on the first, the third, as well as the 10th. These are going to be different. They require a lot of energy in gluconeogenesis to kind of work around, so we have some different enzymes and other factors in play. But other than those steps, it's basically just the glycolysis reactions, but in reverse. All right, so let's look at number 10 first here. Number 10 in glycolysis was this reaction where we had phosphoenolpyruvate. And when we had this molecule, we were trying to get to pyruvate and ATP. This is glycolysis, and the enzyme that was used was pyruvate kinase. However, in gluconeogenesis, we kind of have some extra steps here for step 10, or the first step in gluconeogenesis. Alright, so pyruvate will be our starting material, and we actually have something new as our product. We're not going specifically back to phosphoenolpyruvate yet. We have this kind of an intermediate step that we have to take into consideration. Okay, so pyruvate will actually go to oxaloacetate. And the enzyme that this reaction requires is pyruvate carboxylase. We're going to be transferring a carboxy group with this enzyme. And we also need biotin in play with that enzyme there. Alright, so once we get to our oxaloacetone, or oxaloacetate, I should say. Sorry about that. It's been a long day. So once we get from pyruvate using pyruvate carboxylase to get to oxaloacetate, we could take our oxaloacetate to our phosphoenolpyruvate via a different enzyme again. This time we're going to be using PEP Carboxykinase. So again, a kinase transferring a phospho group, and when we use this enzyme, we do get to our phosphoenolpyruvate. Alright, so after those steps where we took pyruvate, used pyruvate carboxylase to get to oxaloacetate, and then we go to PEP carboxykinase as the enzyme that gets us to our phosphoenolpyruvate. Now we have a bunch of similar steps until step 3. Okay, so let's review step 3 in glycolysis, which was fructose 6-phosphate becoming or transforming into fructose 1,6-bisphosphate. And the enzyme in play was, of course, pKa, also known as... Sorry, that's wrong. Sorry about that. Fructokinase. had them out in order. There's, yeah, phosphofructokinase. Sorry about that mishap there. I was thinking of a different enzyme or something. I don't know. But fructose 6-phosphate uses the enzyme PFK1, or phosphofructokinase, to get to fructose 1,6-bisphosphate. That's step 3 in glycolysis. However, again, in gluconeogenesis, to overcome this large energy requirement, we have to use a different pathway. What we're going to be doing is taking our fructose 1,6-bisphosphate, and we are going to be taking it back to fructose 6-phosphate for here, but we need a different enzyme. So actually, I need to draw my arrow like that. We're going to be using the enzyme fructose 1,6-bisphosphatase 1. So that's F16BP1. That enzyme is going to take us back to our fructose 6-phosphate in gluconeogenesis. We have one more step that's different than our glycolysis pathway, which is going to be concerning step 1, where we just had glucose going to glucose 6-phosphate. And here, usually we would be using hexokinase. However, like these previous steps, like step 3 and then with step 10 of glycolysis, we had to use a different pathway to overcome the energy requirement. So we're going to be using another enzyme to treat our glucose 6-phosphate back to glucose. This enzyme is going to be glucose 6-phosphatase. A trick here is these last two, so like fructose 1,6-bisphosphatase 1, it has the name of the reactant when you're using gluconeogenesis. That's a helpful hint right there, I think. There's, of course, that regulation step, again, concerning step 3, like we were talking about in the glycolysis video. So step 3, again, has the fructose 6-phosphate go to fructose 1,6-bisphosphate using PFK1. And when we were talking about the regulation here, we were also mentioning how if we had this molecule called fructose 2,6-bisphosphate, this would drive the reaction forward if we had that fructose 2,6-bisphosphate also present. So, like we were talking about earlier, we could have our fructose 6-phosphate go to fructose 2,6-bisphosphate, this right here, through this enzyme that has like two domains. One of the functions is the phosphofructokinase 2. Them out of order, sorry about that. That would get from our fructose 6-phosphate to fructose 2,6-bisphosphate if we use PFK2. This is going to happen in the presence of insulin. However, we could also have a reverse reaction again here, a regulating mechanism here to use the phosphorylated. So this is going to have phosphorylation. The enzyme, when it's phosphorylated, it will be this active fructose 2,6-bisphosphatase 2. And when we have that phosphorylated, it's active. We also have glucagon also in play from the liver. And when these components are at play, we have our fructose bisphosphate, go back to fructose 6-phosphate. So that's one of the regulation components of gluconeogenesis. Thanks so much for tuning in, and please do something nice for someone.